And for example, as David spoke, when you have Laplace equation on each on the boundary, you need, if you want to use, for example, Green's representation, you need both boundary values, but a well-posed problem gives you only one. So Dirichlet-Neumann map means determining, constructing, whatever, the unknown, you see? Okay, what people haven't emphasized is that Dirichlet-Neumann map appear also on evolution equations, you see? And I became aware of this when I was a young man, you see, in 1982. And I will tell you the story just because, you know, just for, just entertaining story. I will tell you the story, how I became aware. And then this tormented me for a long time. And finally, there was, I think, a breakthrough in 1997. And this breakthrough was a way to determine the Dirichlet-Neumann map for nonlinear integrable evolution equations. Okay? However, I had already that happened in 1997. However, I had already the great fortune to work with Israel Gelfand, the late Israel Gelfand. In some sense, everything I've done since I met him is strongly influenced by him or due to him. And during our interaction with Gelfand, I had understood that you cannot understand a nonlinear problem without understanding its linear version, you see? So immediately after this formula was obtained, I went to the linear limit, expecting I would recover something which I already knew, and the big surprise was that I didn't. I got something new. And this gave rise what appears to be now a new method for dealing with linear PDEs. And although the first results were for linear evolution PDEs, then there was impact on linear elliptic PDEs like Laplace. And the third lecture, I will talk about our treatment of the Dirichlet-Neumann map, not only for flat bottom, but also for any bottom. Okay, so this is basically my connection and why I'm in here. I can now state that maybe your time will not be wasted because Bernard de Koning, with two students of his, wrote an article on the evolution part of this method to SciAm Review in March, and there was an editorial accompanying this article which said very nice things about this method. So, for example, it says that this Fourier introduced these things, and then we thought everything we could do this so easily that we thought we could not do better. And he compared the situation with, as you know, the high jump. But then in 1965, Fosbury introduced Fosbury flop. I remember this Olympics where this happened. And the editor at least compares this new approach to PDEs with the Fosbury flop. Of course, I always thought that we should not anymore teach PDEs, at least linear PDEs, the way we do. And I will try now to give you a review of this method. The first lecture will be on evolution equations, but the ideas, as I said, I mean, this method is called sometimes a unified transform, and the idea is that one should follow similar steps independent of the type of equation, you see. So although I will first talk about evolution equations, I want you to please bear in mind that the basic ideas will also be valid for elliptic PDEs, which I will talk on the second lecture, and then finally in the third lecture, I will be more specific to the water waves problem. So this is the idea. Let me now give you a little bit of motivation, how this problem came about, how this method, but then I will give you concrete understanding. So by the end of this lecture, you see, by the way, one of the great things about this is very, very simple. I mean, it's more simple than what we do now. So by the end of the lecture, hopefully everybody should be able to use this, okay? All right, but a little bit of motivation first. There is a class of nonlinear PDEs which are called integrables. And these nonlinear PDEs, most of them, I mean, the usual situation is in 1 plus 1. That means one space and one type. And if you if you are not in this area, at least I hope you have heard equations like nonlinear Schrödinger and KdV, both of which, by the way, come out of water waves if you go further to what David was doing. Okay, so these equations are very special. I'm not going to talk at all about them, but the only thing I'm going to say is that, of course, if you take an equation out of a hat, out of a whatever bag, it will not be integrable. So what makes this NLS and KdV special? What makes them special is the fact that you can write them as the compatibility condition of a linear pair. Okay? A very strange fact, by the way. I try to teach courses in this no student would understand, you see, naturally, because you see the brain thinks by associations, by analogies. So if you haven't seen anything like this, it's very strange. Okay? And this is the situation actually. That's what I said earlier when I met Gelfand in 1990. You know, not that many, we worked together for a month. Gelfand says, "Do you understand integrable equations?" I said, "Of course, I understand." You know, this was the only thing I was doing at the time. He says, "Good, because I don't understand anything." You see, so I thought he was joking because, you know, one of the key facts in this is so-called Diaghilev-Marchenko equation. But of course, people have different understanding, and Gelfand, being very deep, you know, needed a deeper understanding than my superficial one. So he pushed me, and out of this, you know, torture, you know, came the realization that the classics had missed something important. And this is strange because, you know, the classics didn't miss much, you know. And what the classics missed is the idea of Lax pair for linear equations, you see. So what we understood with Gelfand is that linear PDEs with constant coefficients also admit Lax pairs. And at least pedagogically, this is very beautiful because now if I teach a course in integrable systems, I do everything at a linear level, you know, and then people understand, you know. So let's start with the heat equation. The heat equation is not a very good example because it's non-linear version or a non-linear version of the heat equation. It's the Burgers equation, which is integrable in an elementary way, not in the complicated way of NLS and KdV. But because this is the problem I will solve, you know, in a new way, just to show you that you can never say something new about the heat equation, which is remarkable because, you know, 20 years ago, I would tell somebody that I have something new to say about the heat equation, you know, they laugh. How can you say something new about the heat equation? I mean, Fourier wrote a book on this, you know. But you can, as you will see, you see. So here is the statement. The statement is forget the heat equation. Instead of the heat equation, look at this equation. Maybe. I have some notes somewhere. Where are my notes? I have some important notes. Here they are. These are my important notes. So yes, this is correct. So I claim that, okay, mu is a scalar function, yeah? And mu is a function of x t k, okay? So if you think of this equation, if you think of this, that somebody gave u, right? So in principle, with some boundary conditions, you can find mu, but then it should be the same with this mu, right? So the system is overdetermined. So in general, you get nothing. So, but you will get something. So this system is compatible if and only if you satisfy the heat equation. Okay? And while I'm talking, there's the homework I talked about. While you're talking, you can do it. You see, you can verify it because if I solve this equation, you know, I have mu x equals I k mu plus u, mu t equals minus k squared mu plus ux plus I k mu. So if I take a t derivative here, it will be mu 2 ut. For mu 2, I use this, yes. Mu tx, mu x, for mu x, I use this. And you will see that they match if and only if you solve the heat equation. All right. So what? No? But it's a fact. Is this a useful fact? I claim it is. Why is it a useful fact? First of all, you know, suppose that I first saw this equation for the first time in my life, and I was asked in some domain, some boundary conditions to solve it. Okay? Then we have fantastic theory, which is called spectral theory, yes? So you separate variables on this. So if I do separation of variables, I will get two ODs, yes? One in x and one in t. Statement number one, the OD in x will be second order, yes? And if I had here 20 derivatives, if I had here 20 derivatives, the OD in x will be 20th order, but this is always first order, you see? Statement number two, you can also think of this as kind of separation of variables because I have two ODs, one in x and in t, but this is generic. Namely, any solution satisfies this property, while the separation of variable solution is very limited, okay? This already gives you something very important because it tells you what? It tells you, you see, if I want to solve this equation by transform in x, you see, it turns out, you don't see this, but believe me, I will not talk about this, it turns out that it is equivalent to performing a spectral analysis of this equation. If I want to solve this equation by transforming t, it's equivalent to performing a spectral analysis of this equation. Okay? But it means that you have a new way of doing spectral analysis, much simpler, because as I told you, you have 20 degrees this first degree. I will not push on that, you see, but this is the connection with integrable systems. The connection with integrable systems is that if the equation is integrable, yeah, this again, similar thing, but instead of having a scalar equation, you have a 2 by 2 matrix equation. Technical difference, you see. So what you do in integrable systems? I already told you that if you want to solve this problem on the full line, yes, you should use the Fourier transform, and if you pretend you don't know the Fourier transform, you will perform spectral analysis of this equation, and out of this will come the Fourier transform. And this is what we did, by the way, with Gelfand in 1990. By doing the spectral analysis of this a la integrable systems, we found a new way to obtain a Fourier transform, which was fantastic because later on we were able to do something similar for a much more complicated problem, and this gave rise to attenuated Radon transform, which was an open problem of medical imaging, etc. We close this parenthesis. Now, in integrable systems, you do the same thing. Namely, you analyze the analog of this equation, the non-analog of this equation, and this gives you a nonlinear Fourier transform. Okay? And this is what you use to solve, for example, your nonlinear Schrödinger. And this does nothing. It's the poor brother. You see? When I was trying, you see, but what happened? You see, but people always criticize integrable systems. They say, look, integrable systems are good, but very limited. You can only do the Cauchy problem. And Julian Cole, the late Julian Cole, with whom I had a very nice, I have had a very nice connection. He was the first student of my former advisor, Paco Lagistrom, and I was the last student of Paco, you know. Came to Clarkson in 1982. Mr. Harvey, your old place, you know, he came to Clarkson and gave for us to solve KdV on the half line. Actually, since you know water waves, you know that the linear limit is not this, but it's this. Of course, this is the unperturbed problem, of course, yes, waves on the right. And of course, if you're on the full line, you can do Galilean and get rid of it, but on the half line you cannot, so leave it there. So he gave us this equation to solve, but on the half line. You see, I remember discussing with Mark Ablovich, who was my mentor at the time. I said, "Oh, Mark, I know how." I don't know how to do this problem, but at least I will get an insight by doing the linear problem, you know, on the half line. Mark said, "Okay, tell me tomorrow what you find." You see, but if you do this, can anybody solve this problem here on the half line? You see, this is my proof that you did well to come to my lecture this morning, to my theory this morning, because this is non-trivial. You see, you might have two ideas, a bad idea and a good idea. A bad idea is to use Laplace transform in T, okay? Why is it bad? It's bad because it's completely natural, yes? Because as you know, Laplace transform, I have to go up to infinity in T, but I want to solve this from 0 to 3 in T, number one. Number two, even if you play these games that play with causality and cutting and all this baloney, you know, you still will have the problem that if I apply Laplace transform, the first thing I will have to do is invert a cubic, yes? cubic algebraic equation. Okay, Ferrari might be whatever, or Cardano, who did Cardano, you know, or Tartaglia actually, but this formula is horrible to start playing with, you know. So forget about Laplace transform. After all, we know it's not the correct parameterization. It's like having your head down and your feet up, you know. So you say, I know that evolution equations need some transform in x. Yeah, this is the correct thing to do. Nice parameterization. Yeah, the parameterization in x will be e to the ikx plus ik cube t minus ik, something like that. You know, this beautiful parameterization. But so you say, so this is what I did, of course. I went to books because you know, to find the transform. Because after all, if it was second order problem, I would do it by sine or cosine, depending on what you have. Yes. But I said, I don't remember a transform. I haven't seen in books a transform for third order problem. But you go and look, nothing. I said, no problem. I was a graduate of Caltech. At the time that Caltech was at its glorious upper limit as applied mathematics department, and I had been taught by none other than Gerald, the late, he died a couple of months ago, Gerald Witham, you know, that you can go from first principles and find your transform. You don't need books, you know. So I went to first principles to derive the transform, and I was perturbed with this, so I went from first principles to derive transform for this problem. Yeah? And I failed. I was very upset. Young guy, you know. Not enough psychological fortitude. I was very upset. So I started calling people. I call Martin Kraskal, the late Martin Kraskal. Martin says, simple problem. I will tell you by tomorrow. Never heard of him after that. Joe Keller. Joe Keller. Thanasis, I'm not surprised you cannot do it. I never like transforms. The only reasonable answer I got was from Stackholt, you know, who had written, I didn't know them, who had written this, you know, these thick books on, and he says, no, Professor Fokas, this is a non-self-adjoint problem, and we don't know what happens, and they may or may not exist. It was very reasonable answer. So, but anyway, this was the story, and I got so upset that I couldn't do this problem, you know, that I left mathematics and I went to medical school. This is true. I mean, one of the main reasons I went to medicine was my failure to do this problem, because, you know, not to be able to do KDV, okay, it's a tough problem, but not to be able to solve a stupid problem like this, I mean, what the hell, okay? So, now, of course, maybe not today, but maybe the beginning of the first lecture, I will tell you a way to do this, very beautiful, very elementary, as it should have been, you see? But what I know now, I didn't know in 1982. So this is the reason. So I couldn't do this problem, you see? So they stayed with me for a long time, and finally, in 97, this is when the breakthrough came. But now, I am not addressing a nonlinear community in the sense of integrable PDEs. I'm addressing a different community. So now I will forget his motivation. So I managed to use half of my time just to tell you stories, but this is not bad, you know. And now I will go back to this equation without any motivation, how it came, and I will tell you the steps that you have to follow if you want to solve this equation or any other linear evolution PDE, like the third order or the 20th order, etc. You see? By the way, you know, Gelfand, being a great mathematician, always tell me, Thanasis, how do you know that what you have done, this, I know applied mathematicians will not agree with the statement, but I will say anyway, how do you know that what you have done is important? If it can be generalized, okay? Already, the method of sine transform, cosine transform is not important because you can only use it for second order, you know, according to Gelfand. Okay, but let's go back to this. Let's go back to this. In this equation, I can take an integrating factor and I can write it mu e minus I k x plus k squared t x equals u e to the minus I k x plus k squared t. And I can do also mu, the same thing. I don't want to write t equals ux plus I k u times e. Yes, I've done nothing. Right? But now, you know, if I take a t derivative here, that should be the same with x derivative here. Yes, which means that I can forget everything. And I say, step 1 of the new method is to do this, namely to rewrite the equation in a divergence form. All right? So all I have retained from our half-hour discussion is that if you give me a PDE, the first step is to rewrite this PDE as a family, one parameter of divergence forms. You may ask why, you see? You may ask why. And this is the step I cannot motivate without this detour, you see? The only thing I can think of is, again, the Gelfand statement that mathematics doesn't like to solve single problems, always like to solve a family of problems, okay? So what I have done, I have taken a simple equation and have written in this complicated form, yeah? For a case an arbitrary complex. You might ask, of course, that how can I do it in general? And the answer is, if you go to these papers, by the way, the Koenig et al. Is Siam Review, March of 2014, and there's a paper by myself and Ewan Spence, again in Siam Review, but I think it's something like September, maybe. September of 2012, where we also do a classic elliptic problem, you know, with the diffraction over a sphere. It's a beautiful story, unfortunately. I don't have time. All right. So then the question is, in general, if I give you a PDE, can you write it? The answer is always. You see, I give you explicit formula in this, which depends only on the omega k. So what you do is you look for a solution of the form e to the ikx plus omega kt, omega k called dispersion relation or whatever symbol of the operator. And from this omega k, you can explicitly compute the coefficients which you will have there. Okay? There's another way to do it if you don't like formulae, which is from first principles. And the first principles is to use the adjoint. You see? So this is the first time I understood, by the way, why adjoints are useful. You know, adjoints are useful because if you write this equation, okay, you write the formal adjoint of this equation, which is this. Okay, and then immediately, as I said, I never understood the importance. For me, that's the only use of the adjoint. You see, formal adjoint, nothing else. From this, of course, by definition, I can do this. So there it is in divergence form, yeah? And then I take the simplest solution of this, which is the exponential, and I have it, okay? That's the most, that's the simplest way. And you use a little bit of tools, the adjoint. Okay. So the first step is elementary, yeah? Now, in the first step,
can I ask a question?
please.
I remember that some review paper wrote actually down the variational principle for this heat equation in the adjoint. So
Who did this?
Rick Salmon did. But anyway, those two have a variational principle, and in one go you get it.
Yeah, I think I will use something like a variation principle in a moment.
For
I
the
believe.
two together.
No, not for two together, only for one. But of course, your remark is absolutely proper. But let me just immediately then go to the second one. So step one is just a PD. Yes, I haven't used anything else now. Yes. Step two, PD and domain. Okay. Step PD and domain. Use Green's theorem. Right? Immediately from there, you can use Green's theorem to obtain a relation between the boundary values. And because this relation contains global information, I have called it global relation. Okay, and if you want, this step two has two parts, 2A and 2B. So let's do this first. Okay, this is a little bit now ambiguity. Let me explain to you what I mean. You see, here is X, yeah, and here is T. So now we choose a domain. So let's take the half line. Okay, so let's take, for example, the half line. And if you do things rigorously, you should also specify what is your T, right? So you should take T to be between 0 and, let's say, and capital T. Yeah? So in general, this thing, yeah? So what I should do, therefore, in general, I should integrate, this is my domain, yes? And I assume, by the way, that things die at infinity. I will make rigorous statements in a moment, you see? So this I should take around here, and if I do this, I will get relations between what? On here, I will only have u, x, and 0, which is my initial condition. Okay? And here, I will have all the boundary values. So here I will have u, 0t, ux, 0t, or depending, so if I have a derivative, a problem of order n, I will have up to dx to the power n minus 1, yes, of 0t. And here, I will have u at t. I'm sorry, at x capital T. Yeah? So this are the boundary values. However, I'm going to cheat now a little bit. For evolution, this would be in the case of elliptic problems. Elliptic is perfect, you see. But here, I am, rather than doing it at capital T, let me do it at T. Okay? This will. So if I do this, then you understand what I will get. Yes, I will get integrals from Green's theorem. I will get integrals from here to here of this function. Yes, integrals from here to here of this function, and integrals from 0 to t of this function. That's it, right? So in our particular case, what you will get u hat of k and t equals u0 hat of k minus, in general, what I call g of k and t, where g of k and t will have, so what is this creature? So this is my global relation. So this global relation, and this is valid for x and t, whatever domain is, but k in C+. So imaginary of k greater or equal to 0. And I will explain that in a moment, why that's the case. Come on. I will explain why it's the case. What is this? So u hat of k and t is the integral from 0 to infinity, e, look at the global relation, at the divergence form, Correct. Remember, we integrated this, yes, and at time t equals 0, this term will go away, yeah? And this, of course, here e to the k squared t. And so I integrate the first term, I will have the integral of this from 0 to infinity, so k squared t will go out, I will get this. This term, of course, you also understand what it is. u0 of k is the integral of the initial condition. Yeah, and this, now you see what it is, g of kt, in our case, will be the integral from 0 to t of e of k squared tau ux of 0 tau d tau plus ik of the integral from 0 to t e to the k squared tau u of 0 tau d tau. So from now on, some notation, I'm going to call this the first derivative, g1, okay? But please note, a key observation only. This doesn't depend on k, depends on k squared. Yes? So this is k squared of t, okay? And this is g naught of k squared t. Okay? Are you okay? Please ask questions.
Only the integral is of k squared, right? You keep
Only the integral. Yeah, outside. Absolutely correct. Bravo. Absolutely correct. Okay. Now, of course, I also see my limitation here. Why I did this? Yes, because this is an entire function for t finite. Yes, these are entire functions, but this is well defined only for k in the lower half plane. Yes, this is the reason for this. Okay. But note one more thing. You see, it is clear that this has nothing to do with this problem. For any problem, see, if I have a problem with 20 derivatives, yes, here I will have up to 19th such creature. I will have 20 things here. Okay, step number 2. Step number 1. Step number 2, you will say, Thanasis, are you kidding us? What is this? This is nothing. I hope everybody sees. You would have obtained this equation how? How could you also obtain this equation? The box, the global relation. How? Give me, Professor He, I see you. Give me another way to obtain this equation. Fast. Time is running out. Take the Fourier transform. Yeah. Take the Fourier transform from 0 to infinity, yes? Take the Fourier transform from 0 to infinity of your equation. But look, Mr. Harvey, if you do this now, you know, you will have to solve, you have to do a lot of integration by parts, yes? And if I had a 20th order equation, I will have to do integration by parts 20 times. While you see already the little advantage of divergence form, no integration by parts, because you build it in, you see? So all I'm saying now is, I'm sure that this equation has been written by many people, at least for a third order problem, but immediately you see the problem. You see, when I do this for a third order problem, you see, I will have in there what? I will have, you see, here, this I know, yes? This I know, correct? Let's think of a Dirichlet problem. Initial data will always begin. Suppose I do a Dirichlet problem. This I know, okay? But this I don't, correct? And if I do the third order problem, it will be worse, because you can prove that in this case, the half-line problem is well posed only with one boundary condition. So here, I will also have G2, the second derivative, which I will also don't know. And in general, I will have something like capital N over 2 plus or minus 1 unknowns. And this is why this Fourier transform approach is not good. The advantage of taking the sign transform at this level is the sign transform will kill this. Okay? So here is the question I pose. Okay? But before I pose this, of course, I can invert this. Yes? So the second statement is, where are we? 2a, 2b, invert. the global relation and deform the contour to obtain an integral representation in integral representation in the complex plane. Okay, so I invert. So I have u xt is the integral from minus infinity to infinity, 1 over 2 pi, e to the I k x. I multiply this by minus k squared t and invert. Yes, minus k squared t u0 of k dk plus or minus 1 over 2 pi, the integral minus infinity to infinity, e to the I k x minus k squared t g dk g of kt dk. Okay, and as I said, up to now I have done nothing new. I have done nothing new because you would obtain this formula by the classical Fourier transform. You see, the only epsilon thing you might say is I cut out a bit of computation by using divergence form instead of integration by parts. But the problem remains because you see in here I have this which I know, and I have part of each which I don't know. And this is where everybody stops. You see? So what is the new idea? The new idea is unmotivated. You see, the new idea. So look how interesting it is. Okay, let me now, for a moment, destroy the sign transform solution. So let me make a remark which will motivate my next step. Let me make a remark which is a very strong remark and will motivate my, leave this here, will motivate my next step. You see, remark. Any solution obtained via classical transforms with inhomogeneous boundary conditions suffers from lack of uniform convergence. At the boundary. This is a huge statement, and I appreciated this statement recently. Let me explain to you. Of course, if you do numerical analysis, you know the statement. You understand the statement very well, but I don't do numerical analysis, so I didn't appreciate it until recently. So what I mean by that? Suppose we didn't use their own transform, which is the Fourier transform here, but we use the sign transform, yes? Instead of this solution, we would have something explicit. Uxt is 2 over pi, the integral, 0 to infinity, sine of kx, yes? And here we'll have e to the minus k squared t u 0 of k, and here we'll have something which I don't remember, some coefficient, and here we'll have the integral from, let's put in front of this here. this is a solution in every single book. Yeah? There is no book on boundary value problems who doesn't give you this solution. All right? And there is absolutely no single book, which is what is bad with applied mathematics, by the way, who proves this. Okay? What do I mean by proving?
When you say proof, you mean?
I will explain immediately. But you see, this is something that, you see, unfortunately, we are not, as applied mathematicians, we are not trained to think properly. This is very, very bad. I will explain in a moment. You see? By tremendous serendipity, Gelfand comes to Greece to visit me in 1990, exhausted. So I said, very good, we can rest. He says, do you want to do some mathematics? I said, okay, let's do some mathematics. So what problem he gives me? This problem. Without anything to do with boundary value problems. So he says, can you solve this problem? I solve. So I do, and I've done this solution. You know? He says, are you done? I said, yes, nice solution, you know? You know this, you know? I know this. He says, you've done nothing. What have I done nothing? Why have I done nothing? And he, of course, was absolutely correct. Why? Because in order to obtain this solution, what do? I start with my definition, all right, of the sign transform, right? And then I take the derivative and I replace by the equation. Do I know that uxt exists? No. Do I know how it behaves for large x? No. Do I know that any of this is legal? Absolutely not. You see, of course, you might say, go to a PD guy, you know, and the PD guy will give you a priori existence, uniqueness, properties of this, and you can do it, all right? But if you don't go to a PD guy, and you want to do, or girl, and you want to do everything from first principles, you have done nothing. So what is the correct logic, which we are not taught, and that's why it is not in a single book. I have looked, I have searched every single book written by applied people in boundary value problems. Nowhere. Look what is the correct proof. The correct approach would be, you know, that Gelfand is right. Namely, I have done nothing, but I'm allowed to postulate this expression. It's my business. I had the inspiration, and I wrote down this. But now, I have to do what? I have to prove, number one, this satisfies the PD. Yes? Number two, it satisfies the initial condition. And number two, satisfies the boundary condition. And then if I have also uniqueness somehow, I'm done at some level. Yeah? So, to satisfy the PD is not obvious, because if you remember, the Fourier transform involves this. If I do the Fourier transform. So it's obvious that it satisfies the PD. Yes? While now it is not. But it's trivial. You will do it. All right? So number one step goes. Number two step. I put here t equals 0. Yes? This dies. And then I appeal to the inverse sign transform, which I know. And it satisfies. So I understand, therefore, that u x and 0 is u0 of x. Perfect. But then I have also to prove that let's call this function okay, that you gave me. I have to prove this. Okay? Right? But of course, you see the problem. Okay? Because if I put here x equals 0 naively, this vanishes. Yes? But we teach students that, you know, that I can take the limit in, yes, if and only if this is uniformly convergent, which immediately tells you that it's not. And this is why this formula not only cannot be generalized to third order problem, but it's useless to do computations, numerical computations. Okay? And far more important, which I realized only recently, this has nothing to do with this problem, Harvey. How we derive a transform for first principles? By assuming homogeneous boundary conditions. Therefore, any transform we will derive, we will have this pathology. Okay? I was teaching a course at Caltech when I was a year there, fellow, and a student asked me this question, and I panicked, you know. I didn't know what to do. And I remember talking to your friend, Alan Newell, and I said, what do we do? And I said, well, I don't know. By the way, this is very serious, you see, because this is what it means. You see, if the books had the correct logic, they would have tried to do this, and they would have realized the problem, you see. So I asked Alan, what do we do? And what did Alan answer? The thoughtful Alan. He says, I don't know, Thanasis, but usually, if we have a problem with uniform convergence, we go to the complex plane. It's the correct answer, okay? So, what I'm going to do now, all this detour was a motivation for implementing the step 2. Step 2, this elementary, but now I'm going to do the following. I'm going to say that replace this contour by this contour. I like DD plus on purpose, okay? Where this, you were integrating along here, yes? But now, you go to the complex plane. And this pi over 4. Okay? Now, this step is elementary. By the way, note, all the criticisms I gave before apply to my method as well. Because again, everything I've done is illegal. But at the end, I will justify everything. You see? Now, this is why? Because look, you see, we're integrating along here. Yeah? So I can do this provided that here I have analyticity. Yes? Analyticity of what function? Let's look at this. So my typical function is GT, is this. I'm integrating from minus infinity to infinity, e to the minus ikx, all right? And typically here, I have the integral from 0 to t, e to the k squared, t minus tau, g of 0, I mean, something here, ux or u, let's say, 0 tau d tau. That's the function I'm integrating, okay? Of course, this function is analytic, yes? Because it only depends on k. Doesn't depend on k bar. So, provided that I have some decay, yeah, I can deform. And boundness at infinity. So the only question is, will this function be bounded in here? Yeah? So look, I have plus should be here, yes? Should be plus here. Where's plus, 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 plus? Where is my formula? Here, it's plus. Okay, plus, of course it's plus. So it's plus here. So this is analytic in the upper half plane, yes? And I have decay because of integration by parts, etc. But I also need to control this. Yeah? So this will decay, you know, when the real part, because t is bigger than tau, that's the important thing. So this is positive. Yes? This is positive. Therefore, this will have decay if the real part of this is negative. And this is the definition of this. So d plus is defined by the imaginary general of omega, which is here k squared, to be less than 0, you see? And also plus means that imaginary of k is greater than 0. And of course, from here, you see that this has nothing to do with this problem. For any omega k, this is correct definition. The imaginary of omega k would be, right? But now I can deform, you see, and I have this. And I can go up to this curve. So now I'm on these curves, you see. Now, it will turn out that this is very important for various reasons. So far what I have done. I have done again almost nothing. Namely, I used the Fourier transform. And I just decided, for reasons which I don't care, to deform the contour to go to the complex plane. I left the real line. But the main problem remains the last 5 minutes. What's the main problem? The main problem that in here, in this representation, there are things which I don't know. Okay? So this is now the third step, which is the novel step of this method. The third step is the third step is use, so step 3, use the global relation to eliminate the transforms of the unknown boundary values. And in this way, obtain an integral expression, because everything now will be known. Okay? Let's see what we mean. You see, first of all, what I said might sound logically strange. Why is it logically strange, David? Why is it logically strange? Because how did I come to this equation, David? I came to this equation by inverting this equation. Therefore, I have used it. In mathematics, we know you use something, you discard it. Yeah? So why am I claiming that you should go back to this? Yeah? Good question, right? And the answer is not the people that know the method. Yeah. the answer is, David, this equation, we use it for what? For real k. But this equation is valid in a huge domain. You see? This equation is valid in the entire lower complex plane. You see?
Imaginary k less than 0.
So we haven't used it yet. Okay? So this is the key. So I will not, I don't want to eat on your, let me just make a philosophical remark and I stop here and I will tell you how this can be implemented tomorrow, but look how interesting it is. You see? Look how interesting it is. When you do a full line problem, so when you have x mounts infinity to infinity, yes, this equation is this. Okay? K now cannot be moved up or down, yes? K is real. Which means that here we don't have theory of complex variables. We have simply complex numbers because K is real. You see? We don't know anything. We don't have any unknowns, right? If I do half line, I have, this. Okay? So now I have theory of complex variables because I have a function which is analytic in the lower half plane. So here is the fundamental logical question. Now I have some unknowns in here. Can I use this additional information? After all, analysis is huge constraint, gargantuan constraint. Can I use this constraint to determine these unknown creatures? No, I don't care about the boundary values, only their transforms, yes? Because in my solution, what I have is this plus ikg1. I don't care about the Dirichlet to Neumann map, really. I care about the transform. Can I use this? All right? The answer is yes. And this is the power of the method. You see? And the third thing, if I do this, now I have this, but I have another term. Because you remember, from the right, I will also have some unknowns. You understand, yes? So I have this now. Double the number of unknowns, yes? However, what is now my Fourier transform? An entire function, yeah? It goes from 0 to L, which means that this now I have a bigger domain. So can I use now the fact that K is an entire function to find these additional unknowns, or again, transforms of the unknowns? And that says yes, and this by algebra. Thank you for coming. More tomorrow. I will know how interesting it was by the number, by the difference between the attendance of today and tomorrow. Any questions are welcome.
I guess the lesson here is we should stick to the real line.
The lesson is you should not stick to the real line. Exactly. The lesson is avoid the real line at all costs, and I will make this very clear. And of course, you know, Summerfield, etc., sporadically, they did this, you see, but only sporadically. What I'm doing here is I'm giving a way to do it systematically, you see? Or Watson transform. You see, what was although, you know, this, if you go to the history, if you go to this other article I wrote with you and you'll see this history, they got it, very people got it wrong, you see, but the moral was right. The moral was go to the complex plane. People didn't follow this. People didn't follow it, which is very strange because you solve, what is Laplace method for all this? Yes? Laplace method for all this is you do everything in the complex plane. What do you expect when you solve a PD, which is a harder problem, to get by with being on the line? It's crazy if you think about it. It's crazy. You see, all the integral representations we obtain for ODEs are in the complex plane. Then you expect to be able to do it for PDs on the real line, Mr. Harvey? Come on.
No.
Very good. Okay, enjoy your lunch.